Today I'm going to talk about a quantum algorithm for edge detection digital grayscale images, as it says on the screen. So, uh, and I will. This work is jointly with my PhD supervisor, Professor Alok Shukla, and Professor Prakash Vedula from University of Oklahoma. So, getting into it. So, what are edges in an image? So, first of all, what we consider an image. An image is just a simple matrix. It's just an array of numbers, and depending on how dense the numbers are, we can count the number of pixel density in an image. So, in our case, we consider an edge in an image. Whatever we call an edge is an sharp change in edges and pixel intensity. So, for example, if you see on the right side the cat silhouette images, it's just a binary image. It's either black or it's white. Now, if you see on the last image, you see there is an outline which is just on the boundary of the cat. Now, this is because there is a sharp change between these two pixel intensities, and since this is a binary image, it's quite easy to detect what the edge is. But assuming if we have a grayscale image, for example, on the left, so there are many shades of gray on this image, and now we need to detect an edge to it. So to precisely define an edge in this image would be again a sharp change in edges and pixel intensities. Also, there is an additional condition that we can always uh, adjust our threshold ourselves on how much on what we call an edge. For example, you can say that if difference between two pixel edges and pixel intensity is about 30, then we'll call it an edge, or we can put it to any arbitrary number. So that's why we have several edges in this image. You can see the edge to the image, and so you can see that this particular roof is not really an edge because it's almost same. So this is what we call formally an edge in our algorithm. Now, this particular definition of taking separation into edges and pixels is what inspired to develop what is called the Quantum Hadamard Edge Detection algorithm. Sorry, I don't know. Okay, it's fine. The Quantum Hadamard Edge Detection algorithm is a very uh, efficient edge detection algorithm for detecting edges in an image. So this is the work on which we built our own work. So I'll just give a brief, very quick review of this particular algorithm. So as I said, image is just an array of numbers which are written like this. So assuming it's a capital F, and what we do is, assuming we want to first just detect the vertical edges. We don't do anything with the horizontal edges. We just want to detect the vertical edges. So what we do is we stack up each column to form a vector of size n1 n2 cross 1. So you see, first column is the upper path, then we have second column, and so on. So we have a n1 n2 cross 1 column element vector. And here the constraint which we are putting is this capital N should be a power of 2 raised to small n. The reason being that we are working in the quantum domain, and we would require this so that we don't have to prepare because quantum works in these regimes. Now, as we have to normalize this particular vector, so what we do is we just create a state vector of this form where each element of small f is an amplitude of the state vector. So if you see here, so m goes from 0 to 2n minus 1, which is the size of this particular vector, and we have to normalize it with some constant, as we have a normalization condition whenever we do such computations. And but the number of qubits it would require I'll call it small n, which is n1 plus m2. Now, overall, this particular quantum image representation is called quantum probability amplitude encoding. Why? because we are encoding our information into amplitude of a state vector. But there are other ways to do the similar thing, which are encoding our information phases as well. And this particular image encoding method is also something which we'll use in our particular algorithm, which I will discuss later. So this particular approach now, which I will discuss further. So this is how I prepare a state before doing any processing on this image. So sorry, if I move ahead and if I show how I will obtain how I'll process this image. Now, since I am just giving a brief view of QHED, everything is in just one particular slide, and I will try to make it using the block diagram method. So this cat small f is the image itself. So I've encoded my image using a technique which I will call small f, and I require one ancilla qubit. I will quickly come to why do I require this ancilla qubit, because it will help in our extracting the information about the edges of an image. So what I do is I start with this f and I create a vector of this form. If you can see that, now here I have written this vector form so that it becomes easier to deal with. And also I just remove these indices of f00 f0, and I'm just calling them c0s, cns or cms. So as I mentioned earlier, that edges are essentially difference between two adjacent pixels. So if I apply a Hadamard gate on a small vector, it's a very simple matrix multiplication. And I find out that there's some uh, some difference which I get between two adjacent values in this using the Hadamard gate. So so naturally I apply a Hadamard gate on the ancilla qubit. The reason being, here I have single pixel values. So it's not easy to take. It will be difficult to take difference very efficiently. This ancilla qubit will help us with this process. So what I do is they replicate each pixel. So C0 becomes twice, C1 becomes twice, and so on. So this ancilla qubit is now used even to store information, which we won't be using later on. So what we have done is we have stacked our image and made multiple copies of pixels. So C0 is the first pixel and so on. Now what I do is this particular matrix, which I call B2N, is what I will call a permutation matrix. So why a permutation matrix? Because it shifts each entry of my vector to an entry on the left. So if you see C0, if you see the first two entries are just for now C0, C1, and this first entry goes to the last entry. Now you can see it's mapped to the last entry, and the second entry becomes first entry. So all the entries have shifted. So that's why we call it the permutation matrix. It permutes the pixel values. And now the last step, where I have to find the difference between the adjacent pixels. This is where I will require another Hadamard gate. So now if I now apply a Hadamard gate on this particular state vector, which is this orange line, after this, what I get is now I have the addition of the first two pixels and difference between the other two pixels, and so on for the complete vector. So now you see that I have a vector for which half of the vector which has the difference between two pixel values, C0 minus C1, C1 minus C2, Cn minus Co, and so on. So here is where I will use the ancilla qubit. So if you see each element, each difference is a second element, which means if I measure the ancilla qubit to be in state 1, I will get just the pixel outputs and nothing else. So I will get just the difference between the pixel values, and you using just one measurement. So I get that the probability of obtaining the edge, which is the difference in edges and pixel value, is 50%. So this is the QHED algorithm, and the major cost, if you can see from this block diagram, the major cost of this algorithm is this the n 2n+1 matrix, which can be performed efficiently using order poly n, where n is the number of qubits. So here there are n+1 qubits. So you can say poly n number of qubits I will require to perform this permutation. So this is the major cost which we will keep in mind when we develop our algorithm. And we will, another thing which we will keep in mind is the Hadamard gates, which will be very useful when we create our own algorithm, when we compare our algorithm with others. So if I go ahead, if we see at this QHD method, it's a very brute force method. We are intentionally obtaining difference between two adjacent pixel values, which seems very non which seems very trivial. There is nothing very quick way to do that. So what we do is we look for how would edges, or how would information about edges look in some another domain. In this case, which a very commonly used domain for image processing tasks for any spectral analysis, is a Fourier transform. So we think about how these edges will look like in Fourier transform. What we find is, in real space, obviously these are sharp change in pixel intensity values, but in Fourier domain, they correspond to high frequency components, which means whenever the pixel, whenever the end part of the Fourier spectrum will store the information about edges of an image. And we obviously know how to perform a quantum Fourier transform, which classically is n log n, which is the butterfly algorithm fast Fourier transform, while quantum is log n square, or if you take in number of qubits, then it's order n square. So we obviously have order n square, which is much more efficient than the earlier algorithm. So if I just naively do this thing, if I just naively take a quantum Fourier transform, somehow separate out the high frequency components, then I will get an edges of an image. And that algorithm is probably around order n square, which is roughly around order n square, if I just can perform the high pass filter using that. But then we see, why should we stop here? We can go even further. We can make an even efficient algorithm. So which is what I will be discussing today. And before I go into the algorithm, I will just show you the block diagram of the complete thing, so that you can get a general idea of what paths which you will see in the ahead. So the first path, which is the purple one, sequency order QWHT, which is Quantum Walsh-Hadamard Transform. I will explain these words coming ahead. There is a high pass filter box, and there is an inverse transform. So you can see it's similar thing which we do in Fourier. We take an image, we take a Fourier transform, we do our processing, which in this case will be high pass filtering, and then we just take an inverse Fourier transform, and we obtain the edges in an image. So this is similar thing which we will do, but we will see why this particular transform is much more efficient than the Fourier one. So what are these Walsh-Hadamard transform which I am talking about? So given this kind of circuit, which is just bunch of Hadamard gates, we can see this is some linear transformation here. So given in vector k, I will get some output, which is essentially a superposition of all the states if we are just initializing in zero state. So this particular formula says that there is some linear transformation which is involved here, which we can use for our further processing. And to do the computational cost of this thing is n log n in a classical computer, because it again relies on the same butterfly algorithm on which the fast Fourier transform works on. But when we see this Hadamard gates act parallelly on all the qubits. So the circuit depth of the complete circuit is order 1. So we have gone from order n log n to order 1. So it's much more efficient than taking a quantum Fourier transform, because quantum Fourier transform is still log n square, or if n is number of qubits, then order n square. So obviously we are doing much better in terms of circuit day for natural Walsh-Hadamard transform. And the reason I call this a natural thing is nothing to do with the name actually natural. It's just that the Hadamard thing, just applying a Hadamard gates give me the solution. So it's kind of natural to see it naturally occurs in these computations. So now, similar to Fourier, there are some bases involved in quantum in this Walsh transform, which I will call Walsh bases. So these Walsh bases you can see here. These are I have given example of some particular limited number of Walsh bases. So there is W1, W0, W1, and these are rather randomly arranged. So in case of quantum Fourier transform or any Fourier transform in general, what we see is the initial components of Fourier transform generally correspond to very less number of zero crossings. So any Fourier transform, as we go ahead in the Fourier, as the spectrum goes bigger, the number of zero crossings becomes bigger because we have sine theta, cos theta, and if we keep compressing it in some value, the frequencies keep faster and faster. So this definitely doesn't seem like this. This definitely doesn't seem like the first one is crossing zero times, but the second one is rapidly increase, going up and down the x-axis. And similarly, there is no proper structure on how we can exploit this thing. So what we have to do is we have to rearrange this in such a way that we can have this in number of zero orderings. So what I do is I rearrange these things. So now if I rearrange these things, the first one obviously is W0, which is zero number of crossings. Second one, now you see, corresponds to one crossing from the x-axis. Second one crosses the x-axis twice. Third one crosses it 3 times, and similarly and so on. So we have gone from this ordering, which is order 1. Now I have to do some reordering, and since we have to do some reordering, it will have some cost on how we perform this reordering. So how do we actually perform this reordering? This reordering is performed using using a particular unit tree, which I call UZ. So how do we come across this unit tree, or how we visualize this unit tree is this circuit transform. But this is not very intuitive. How do we come across? So what we have to do is we have to look at the Hadamard. We have to look at the sequence or the Walsh-Hadamard transform. So if I go a couple slides further, this is my Hadamard transform, which is H and K, and there is -1 raised to m dot k and the basis vector. Now it's a very simple thing, but if we have to do this reordering thing, it becomes a little complicated. But there's one thing which we notice. There's a C0 gate which is here somewhere hidden. So obviously we require some C0 gates to perform this reordering. And again, there is some swapping of gates because it was earlier m dot k, which is just bitwise multiplication, but here I am going from backwards. So obviously we require some swap gates. So what we do is we apply these Hadamard gates, and then we start our process of reordering the basis itself. So this particular UZ is realized by taking C0 gates in succession one by one, and then applying swap gates in parallel. Why? Because swap gates can be applied parallelly, because the first swap gate, which is this particular swap gate, and this particular swap gate doesn't have any connection with each other. So we can perform all the swap gates in parallel, but C0 gates have to be performed one by one, and so the major cost of this algorithm comes from the C0 gates. So if I have an n qubit vector, I will have n number of C0 gates, or assuming I'm being more precise, it's n minus 1 number of C0 gates, but you can always say it's an order n number of C0 gates, where n is the number of qubits. And earlier we have seen that to have an image of n1 cross n2 to be encoded in this particular setting, we would require order log of these circuits, a log of these qubits. So considering all of this, we obtain an order log to n number of log to n complete circuit depth from Hadamard to here. This is the complete circuit depth which will require to perform the sequence order Walsh-Hadamard transform. So earlier, our natural order Walsh-Hadamard transform require order n, but since we have to perform our edge detection in such a way that we can obtain the high frequency components or high frequency components, I will have this additional cost which I will have to bear. Now, once we have this, once I have encoded my image using the quantum probability image encoding, and then perform the sequence order Walsh-Hadamard transform. So if I'm just ignoring right now on how to prepare the state using quantum probability image encoding, and just focusing on the core path processing path of the algorithm, this is the only major task which we have to perform. Now the other path is isolating the low frequency components and high frequency components. So I have to isolate both the spectrums. So how do I do that? To do that, we have something called the high pass filter. So high pass filter passes high frequency components from frequency order Walsh-Hadamard transform. So assuming to create this particular high pass filter, I use that ancilla qubit or the indicator qubit which I have shown in the block diagram here. The block diagram here, I will be using this ancilla qubit. So to obtain this to use this high pass filter, assuming I have a vector of this form, and I need to separate out some certain components. Assuming I have to just remove the first C components of this particular vector, and given I've been given this particular state vector, what I do is I create this unit tree, which is something like this, and I create this P bra P cat P output operator, which acts on my ancilla, which acts on my circuit. So one is the ancilla qubit which he had shown earlier, and it is tensor product with the Ks, which is the sequence order transform which I had already obtained. And if I pass it through this, you can see it will retain the X gate will act on the first L components which were earlier described, and the and the rest of the components will just pass through. So sequence ordered, we have been able to separate out high frequency and low frequency components using this particular method. So if I see again, if I look at the circuit once again and compare it with the explicit gate transformation, you see this QPIE, which is my image encoding technique. Is there a question? No. Okay. So if I have to look at it, QPIE is my image encoding technique which I use to encode my image into my state vector. Sequence order Walsh-Hadamard transform, which is this particular circuit between these two red dashed lines. So I apply Hadamard transform, which was my order 1 complexity thing. I apply this rest of the C0 gates and swap gates, which is the UZ component which was used for reordering. And then we have high pass filter. In this case, I have used high pass filter, which is just one C0 gate. So what this one C0 gate does is it will separate out the first half and second half of the frequency spectrum. So what it will do is, if I let's say assume I have n components in the vector, it will take half of them in it will take half of them with ancilla qubit 0, and other half will be ancilla qubit will be attached to ancilla qubit 1. So this C0 gate in this case will perform my high pass filtering. Then I have to again go to my real domain to obtain my edges. No, I mean it's always possible to keep it in Walsh domain, but it's always preferable to take it in the real domain. So what I do is I take inverse of UZ, which is just again bunch of swap gates and bunch of C naught gates. So this time the swap gates have to be uh, applied a little differently, but again this again is a order of n. So if I naively calculate it, first block, which first purple block, has a complexity of order n, where n is the number of qubits. Second one is is here is just one particular C naught gate, so it's not really any complexity. But again, it's just order n complexity. If I want to perform this high pass filter in general, it will have a multi control C naught gate to obtain this filtering. Then I have again sequence ordered inverse quantum Walsh-Hadamard transform, which is again order n. So doing all of this together, and now I have an ancilla qubit. So using this high pass filter, I had separated out the low frequency components where the ancilla qubit will be 0, and high frequency components where the ancilla qubits will be 1. So what I will do is I will measure this ancilla qubit in ket1 state, and hence obtain this particular quantum state, which will be in complete, which will contain all the information about the images without disturbing this particular state. So what you can do is you can measure the ancilla qubit and just use use the information about these edges in some other image processing tasks. So we don't really have to disturb qubits at all. Qubits which store the data at all to actually get the output, which is one of the very major achievements in this thing, that we don't really have to tamper anything with the data qubits. Okay, so going further, these are some examples of examples using the algorithm. So here, if you see, there's an 64 cross 64 computer generated string image. These are these are again generated such that we are just getting the edges of something and nothing else. So the reason to do this is to get a numerical comparison between our algorithm and the QHD algorithm. You would require some numerical value, and the best way to do it is using generating edge image which already contains edges of an image. So we can use that as a base for our SSIM scores, and we have done it for several images. So this particular first image is also generated using Python in computationally, and you can see after applying our algorithm, we obtain this image. Now obviously these both are same. It's because we are just detecting the change in the pixel values, so these both are supposed to be same. Then we have done the similar thing using QHED algorithm, which was earlier described, and we have done for polygons as well, which is given here. What we see actually using after performing these computational tasks is the SSIM scores don't really change much. So SSIM scores using our algorithm and the QHD algorithm is almost the same, but the advantage here is that the circuit depth is of our algorithm is much less than the earlier QHD circuit, and the techniques which are used for image encoding, the techniques which are used for measurement, are exactly the same where as the QHD algorithm, and yet we are able to obtain much lower circuit depth. Now these images are very small images. These are 64 times by 64 by 64 images, which are not really big images. We have much bigger images in real life. So what we do is we apply this algorithm to some real life to some images which can be seen here. Now this particular image has some blobs of coins dropped, and it's again a black and white image, and you can see it can detect the edges. The advantage here, and the reason that we have not performed QHD on this algorithm, is because this particular image is of size 512 by 512, and the QHD algorithm doesn't run as fast. The QHD algorithm is not as efficient to work on our particular systems on which this computational examples were performed, and yet our algorithm worked fine. So what we see here is in our daily normal working laptops or computers, these algorithms have certainly much difference because they don't perform very well or they can't store enough information for simulations as well. And similar, so again, these are the images on the right are bigger size images, and we have found these examples. And now we look at the circuit depth analysis of these particular algorithms. So again, we compare it with Fourier transform because Fourier transform is a very natural transform which we use for all image processing tasks for classical and quantum both. So it's very natural to compare our algorithm with some quantum Fourier transform thing. So if I am assuming that n is the number of qubits which we are requiring, then a quantum Fourier transform will require order n square circuit depth. A natural order quantum Walsh-Hadamard transform will require order 1, which is just bunch of Hadamard gates, and the sequencing one will require order n. So even by just even after applying, even after reordering, I'm still getting a circuit depth which is quadratically faster than a quantum Fourier transform. So naturally, one has to realize that Walsh transforms are more natural for performing computation on a quantum computer rather than Fourier transforms. So and then we see the we compare the circuit depth of the earlier algorithm, which was Quantum Hadamard Edge Detection algorithm. And as I said, the major cost of that algorithm came from the permutation matrix, which shifted the indices of the vector. And for that, the cost to perform this particular permutation matrix is order polylog n, while our algorithm, the major cost is just sequence order Walsh-Hadamard transform. And even in that particular algorithm, the major cost is just the reordering of the basis functions. This reordering is done as order n, so that's the only major cost which we see in our algorithm rather than the other parts of this algorithm. So we obviously there's a polynomial increase in our polynomial increase in the advantage in this approach rather than the quantum Hadamard edge detection approach. And with this, I would like to end the talk. And these are some of the important references. Now, one can obviously read more about these things. We read more about Walsh functions using with the seminal paper by Walsh himself, which was given in 1920s, and more about the quantum advantages or quantum implementations of this Walsh basis function in literature. It is used in many places, such as neural networks as well. So yeah, these are some of the references which I've used for my work, and thank you. And this is a QR go to my website if you like to read further about this paper. Thank you. If there are any questions, I will be very happy to answer them.